Hello everyone, my name is Mohini Pandey. Today we are going to explore a smart and efficient disk scheduling algorithm that plays a key role in operating systems and data management, the CLOOK disk scheduling algorithm. This presentation will not just explain what CLOOK is, but will also compare it with other algorithms, dive into how it works internally, visualize its efficiency, explore its use cases, and reflect on its limitation. Let us start with the fundamental question, why do we even need disk scheduling? Hard disks are mechanical devices. The read and write head must move physically to access data on different cylinders or tracks. This movement is called as seek time and is a major bottleneck in data access. When multiple processes request disk access, the system must decide in which order to fulfill them. The poor scheduling increases seek time and degrades system performance. The disk scheduling algorithms aim to minimize this head movement, improve throughput, and ensure fairness among requests. CLOOK is one such algorithm, efficient, fair, and widely used. How CLOOK emerged. To appreciate CLOOK, let us take a quick tour at its precedents, FCFS, SSTF, SCAN, and LOOK. FCFS, first come first serve. It is a simple and fair but very inefficient. SSTF, shortest seek time first, chooses the nearest request reducing the movement but can starve the distant requests. Scan, the head moves back and forth like an elevator, serving requests along the way. Look, an optimized scan. It reverses only when there are no more requests in the current direction. Then comes the CLOOK, also known as circular look, which does not reverse. Instead, after reaching the last request in one direction, it jumps back to the lowest numbered pending request. This avoids the unnecessary travel and improves its predictability. What is CLOOK? CLOOK is a unidirectional circular disk scheduling algorithm. Let us break it down. Unidirectional. The head moves in one direction. Circular. After reaching the last request in that direction, the head jumps to the first pending request. So instead of the disk going edge or reversing, it loops back intelligently. This makes it more efficient, particularly in large disk systems or busy servers. It prevents starvation. The circular approach inherently helps in preventing starvation for the request located at disk extremes, ensuring all requests eventually get serviced. Let us see how CLOOK works step by step. Unidirectional sweep. The disk head initiates movement in a single direction, for example, towards increasing the cylinder numbers, reversing all pending requests encountered along the way. Last request stop. It continues this methodical sweep until it fulfills the very last request in that specific direction, without continuing to the absolute end of the disk. Efficient jump back. Upon reaching the last request, the head performs a swift and non-deceiving jump to back the closest pending request located at the beginning or opposite end of the active request range. Continuous serving. Once repositioned, the head immediately resumes servicing requests, continuing its movement in the original direction, thereby completing the circular process. Let us see how CLOOK works. Visualization of CLOOK. Let us visualize it with an example. Let's say the head starts at 100. Then it moves and all the pending requests it has are at 55, 58, 60, 90, 150, 160, 184. It moves from 100 to 150, then to 160, then to at 144, 184. Then it jumps to 55, not to 0. And then it serves from 55, 58, 60 and 90. This is CLOOK working. Now, the jump helps save time compared to scan or look, which may go all the way try and track to 0. Advantages of CLOOK. Why do we even prefer CLOOK in many systems? Because of many reasons, such as reduced seek time, fewer long distance moves, especially on large disk. Another one is uniform wait time. Every request is treated similarly, reducing the bias towards certain positions. Another point, low computational overhead. Sorting the request queue and performing a jump is fast. Fairness. No request is starved. The head eventually loops back to cover all them. Great real-world performance, especially in workloads with uniformly distributed or cynical access pattern. Now let us look at the disadvantages or limitations of CLOOK. Look, CLOOK isn't perfect, such as not always optimal. Algorithms like SCAN, FSCAN may outperform it in specific scenarios. Not ideal for real time. In hard deadlines, even the circular delay may be too long. Inefficient for clustered requests. If most requests are in one small area, the jump may feel unnecessary. Slightly complex to implement. Compared to simpler algorithms like FCFS, it requires sorting and head tracking. In summary, while the highly efficient in many general purpose scenarios, CLOOK is not a one-size-fits-all algorithm. Now let us see how CLOOK compares with other algorithms. FCFS, Server's Request in Arrival Order. In comparison to CLOOK, CLOOK is significantly more efficient due to the minimized head movement. FCFS movement pattern is arbitrary. Scan. Scan's movement pattern is full sleeve. CLOOK is generally more fair and avoids unnecessary full sweeps at the disk's end. Look. Look's movement pattern is it stops at the last. In comparison to CLOOK, CLOOK is a circular variation, offering better starvation and prevention by jumping back to the closest pending request. CScan. Its movement pattern is circular to end disk. CLOOK offers a more uniform seek time than SCAN, but is more efficient than CScan as it does not sweep to the absolute end of the disk. SSTF. Its movement pattern is closest request. CLOOK avoids the potential for starvation inherently in SSTF by ensuring all requests are eventually serviced in a predictable manner. CLOOK sits in a sweet spot, which is efficient, fair, and reasonably simple. That is why it is often the default choice in operating systems. Now let us look at the real-world application of CLOOK. Where is CLOOK used? CLOOK is used in operating systems like Linux and Windows, in database engines like Oracle's, file servers and RAID controllers for predictable file access patterns, in virtual machines to balance the input-output among concurrent users, and in embedded systems where tight seek efficiency is needed with low CPU overhead. It is a balanced design which makes it ideal for multi-user high-load environment. For virtualized environment, it's key for managing concurrent disk access requests from multiple virtual machines on a single physical host, ensuring a fair resource allocation. Now let us look at the theoretical analysis of performance matrix. Total seek time, sum of distance the head move. Average seek time, total seek upon number of requests. Throughput, request serviced until per unit time. Fairness, equal opportunity for requests regardless of position. CLOOK excels in average seek time and in fairness, especially compared to other algorithms like SSTF or FCFS. In benchmarking tests, it consistently is close to optimal in general workload. Conclusion. To summarize, CLOOK is an elegant optimization over other algorithms like Look or Scan. CLOOK is balanced performance in effectively fairness. It's widely applicable in real systems from PCs to data centers. But as with all algorithms, it is not perfect. The best scheduler depends on context. Still, CLOOK remains a gold standard in disk scheduling due to its practical and simplicity. Now that we have understood the entire CLOOK disk scheduling algorithm, there is a small quiz for you all to answer. Let us start with the first question for the basic understanding. What is the primary goal of disk scheduling algorithm? Option A, to increase memory capacity. Option B, reduce seek time. Option C, eliminate file fragmentation. The correct answer is option B, reduce seek time. Next question. In CLOOK, how does the head behave after servicing the last request in one direction? Option A, reverses the direction immediately. Option B, moves to the end of the disk. Option C, jumps to the closest pending request in the opposite direction. Correct answer is answer C. Another question. CLOOK is best described as option A, primitive algorithm, option B, unidirectional and circular algorithm, option D, greedy algorithm. The correct answer is option B, unidirectional and circular algorithm. Another question. Which algorithm is most similar to CLOOK but reverses direction instead of jumping? Option A, FCFS, option B, SSTF, option C, LOOK. The correct answer is option C, LOOK. Why does CLOOK reduces the chance of starvation? Option A, it uses priority queue. Option B, it preempts active requests. Option C, it always returns to the lowest pending request. The correct answer is option C. Another question. CLOOK is commonly used in which of the following systems? Option A, mobile phone GPS system. Option B, antivirus scanning algorithms. Option C, hard disk input-output management and operating system. The correct answer is option C. Another question. CLOOK typically offers option A, higher seek time than FCFS. Option B, lower seek time than LOOK. Option C, same seek time as SSTF. And option answer is option B, lower seek time than LOOK. Another question. Which of the following is the disadvantage of CLOOK? Option A, ignores clustered requests. Option B, too simple to implement. Option C, causes starvation. The correct answer is option A, ignores clustered requests. Another question. CLOOK requires the request queue to be option A, in a random order. Option B, sorted based on arrival time. Option C, sorted in ascending orders of cylinder numbers. The correct answer is option C, sorted in ascending order of the cylindrical numbers. I hope you have understood the entire concept of CLOOK disk scheduling algorithm. If you have any doubts, leave them in the comment section below. Thank you so much.